Hello, everybody. Welcome to my today's talk. My name is Łukasz, and I work at Software Dimension, and for the last almost 2 years, I've been working on development of Membrane multimedia processing framework. And today, I would like to share some of my experience with you. Okay, so just to start with a brief agenda of my today's presentation. First, we will try to answer the question what pipeline is. Then, and especially, we will try to focus on the usage of pipelines in multimedia processing. Then we will answer the question what membrane is. And I will try to somehow leave this with a live demonstration. And then I will talk about how we solve some problems with pipelines in membrane. Okay, so let's get started. So generally, what are we going to talk today? We will be talking about pipelines. What are pipelines? Actually, this is a pipeline. Here is a pipeline. Here used to be a pipeline. And some. But we want to discuss pipelines in context of computing. So I have found some nice definition, and I would like to quote it. But the pipeline consists of a chain of processing elements that can be like processes, threads, coroutines, functions, arranged so that the output of each element is the input to the next. And as you can see on this picture here, we have some kind of data source that reads the data from some kind of outside world, then a couple of processing elements, and finally some kind of data sink that is capable of writing this data to the outer world. And pipelines are all about data processing. And these abstract concepts of a pipe, which is like between particular elements of a pipeline, is a representation of this interface that you are putting the output of one element as an input to the other. Okay, so in case you are not encouraged that pipelines are cool, I would like to highlight some cool features of pipelines. So apart that they deliver gas, they also encourage composability. And we can see that we might have like a couple of small components that are linked together. And the cool feature of a pipeline is that first, we can link these elements like seamlessly because no adapters are needed because the pipeline's interface already defines that they can be connected together. And another cool feature is that such a big component can be treated as in the same manner as some small components. So the user of such a big component only needs to know how does this big component transform the input and what is put on output. On the other hand, pipelines also encourage decomposition. So you might have some complicated stuff and split them into several independent steps. And in case you're familiar with like a design of concurrent algorithms, you probably know that the very first step of designing such an algorithm is to perform a partitioning of this problem. You can do it either in a domain way or in a functional way. And pipelines are a way to actually perform this functional decomposition. No wonder pipelines are used in multimedia. Here are some examples like GStreamers, Microsoft Media Foundation, and before mentioned Membrane. So just to give you like a view on how such a pipeline can work, here is like a very basic, however commonly used example from GStreamer. So we have like a kind of file source that reads data from file system. Then this data is put to a demaxer that separates two tracks, audio track and video track. And both these tracks are then put to appropriate decoders. And once we have decoded data, we can play it with an appropriate player, like audio sync player or video sync player. Okay, when it comes to Microsoft Media Foundation, let's just skip it. Actually, I have put this picture here because when I was searching for some kind of information about it, to give you like a nice example, I think the third result in Google that has appeared was an eBay action that sells this Media Cream Foundation. So I've just put it here. So we won't go deeper into it. However, we will look under, now I would like you to wave hello to Membrane. So how many of you have heard about Membrane like before this presentation? Yes, I can see my clip. Okay, great. So what Membrane is? Membrane is an open source multimedia processing framework. It's written in Elixir and run on Erlang's virtual machine, which is called Beam. And it consists of two main parts. The first part is membrane core, which somehow delivers tool to create your own processing elements, as well as to connect these elements and force some kind of pipelines. When it comes to the second part, it's called plugins, and these are some kind of processing elements that can be used by the user of a framework. So what plugins do we have? We have a couple of them. You can see here that there is a bunch of plugins. To summarize, I have prepared this slide. So we support multiple network protocols. You can read the names if you want. I don't feel like doing so. We also support multiple both audio and video codecs. So we deliver encoders and decoders of these codecs. We also support different multimedia container formats. We also allow for some multimedia manipulation, both for audio tracks and video tracks, as well as we deliver some common functionalities that are more like media agnostic. So we can have like a real timer that turns the offline processing into online processing, file source, and the T and the funnel. What is T and the funnel? Well, actually this is T, and this is funnel. And I think that based on the shape of these elements, you can guess what kind of processing happens with the stream that is put into them. Or at least I hope so. So now let's look under the membrane's hood. You need to know that since membrane is written in Elixir and run on Erlang's virtual machine, it's somehow dipped into the actor's model. And actor's model of processing is a concurrency model of concurrency, actually. And it relies on like some fundamental rules. So the first rule is that there are like multiple actors that are running concurrently, as you can see on this picture. For each of these actors, there are some events that are happening. And when we consider events that happen for a particular actor, we can determine their order. That's not necessarily true when it comes to events that happen among different actors. Another thing is that actors can also determine their behavior as a way to react for events. And also actors can send messages to each other, so they can communicate as well as an actor is allowed to spawn another actors. So how can we use this concurrency model to model media processing? Well, this is how. This is like the very basic scheme of an element's lifecycle. So first, after some initialization of this element, we enter such a loop. First, we wait for some data to be received. Then we process this data. Then we send this data to some other element, for instance, and we update our behavior. So what the user is actually interested in doing is this processing part. And this is why in membrane, we allow user to define his or her own processing method. It's done with the use of callbacks. So this is like the code snippet with an exemplary callback implementation. And this function will be called each time a new data arrives for some element. Some important things to note here is that this is like a pure function, or at least it's good when it's a pure function, because it simplifies the debugging. And when we want to have some side effects, like communication, we only declare our will to do so. So as you can see, as a part of return value, we declare that we want to communicate with the other element and send the data further. Once we have a couple of such processing elements, we can connect them together. And here is a code snippet that shows how the elements can be connected. Like an important thing to notice here is this pipe operator, which is actually something that builds our pipeline. And this is what happens under the hood when we extend these life cycles, or at least a couple of these cycles. We can see that, for instance, we have the first element, the data is delivered to this element, processed, and sent further. And this is how basically pipeline works. Okay, so let's continue with a live demo. I have prepared actually 2 pipelines. And we will be sending data with the use of RTMP. So we're going to have an RTMP sender and RTMP receiver. Okay, so this is how our first pipeline looks like. This is the sender. So we basically fetch some encoded video and audio representation with the use of HTTP source. Then we fetch some interesting information, for instance, sample rate for audio track or resolution for video track. Then we turn the processing into online one with the use of retimer. And then we use RTMP sync to send it via network. And here is like the other side of our system. So here we read the data from network with the use of RTMP source. Then since this data is already muxed into a container, we demux it. We have 2 separate tracks. We add this additional information like resolution and sample rate for the appropriate tracks, and we play it with a player. Okay, so now I will make an attempt to run it. Actually, what happens here is basically definition of this pipeline, and here is the structure of a pipeline. So this is basically something that reflects the structure I have discussed previously. Here is just a way to listen at a particular port. So we're just gonna skip it and run our sender. And when it comes to the receiver, we can see that in our player, which is visible on in this Livebook, something starts playing. Okay. Yeah. I think you might be familiar with this track. Okay. So let's continue with the presentation. I hope it will start displaying here. Okay. Here we are. Okay, so let's go to the Pimp My Pipeline section, and I will try to show you how we solve some problems with pipelines in Membrane. So as you can see, pipelines might be complicated. This is a complicated pipeline, and I won't point with a finger which products that is based on Membrane actually has such an internal structure. However, it has already been discussed today. But let's go further. So let's design a very simple processing pipeline. So as we can see, we have 11 processing filters. Let's also set some time constraints so that we can reason about this processing. And let's assume that each filter processes a particular buffer with data within 200 milliseconds. And in order to be able to tell whether the processing happens at a satisfactory pace, we need to define some kind of metrics. And I would like to propose 2 of them. The first is throughput, which is a number of buffers that are processed by a pipeline in a given time. And the other one has a long name, however, I think it reflects what it is, which is the average time spent by buffer in a pipeline. So the time that has elapsed between the buffer was sent by a source and received by a sink. So here is how the value of the throughput metric changes overall the runtime of pipeline. And we can see that after some initial warm-up, it converges to a very particular value of 5 buffers per second. Why 5 buffers per second, you might ask? Well, you cannot actually exceed the throughput of the slowest element of the pipeline. And in our case, each element is processing 1 buffer per 200 milliseconds, which adds up to 5 buffers per second. So this is why we stabilize at this value. And here is the other metric, average time spent by buffer in pipeline. And it's also not surprising that this value will be something around 2,200 milliseconds, because all the time spent by buffer in a pipeline was spent on processing it, and we had 11 elements that were processing 200 milliseconds each. So this is the result. However, it was a perfect situation. All the processing was perfectly synchronized. And it does not happen in real life. In real life, we almost always have like this one lazy element that is processing much slower than the others. So here is like a visualization of this problem. We can see that the last filter, the 11th filter, is now processing a buffer within 500 milliseconds. And what consequences does it have? Basically, when it comes to throughput, we can expect that it will decrease, and now it stabilizes at around 2 buffers per second, but that's also something we can expect because now the slowest element processes 2 buffers per second, so we cannot exceed this limit. However, when it comes to average time spent by buffer, we can see some unwanted tendency because this value doesn't seem to converge at any point. It simply steadily increases. And it might, well, of course, this is connected because now the buffers with data are waiting before the slowest element. And the longer the pipeline runs, the more buffers will be in that queue. So that's because this value increases. However, it might have some other consequences, like increase in memory usage, because of course this queue also is somewhere in the memory. So when we need to have the bigger queue, we end up with a greater memory usage. So how can we solve this problem? Well, we can solve it. Oh, I thought that it will be visible better. However, I can tell you that we can solve it with a back pressure mechanism. So what is a back pressure mechanism? We need to now we now need to prevent buffers from sending, prevent the filters, of course, from sending buffers until they are like explicitly told to do so. And this way to tell a filter to send buffer is sending a kind of a message. In membrane, we called it a demand, and this is represented here with this blue arrow, which is traveling through the pipeline. So as you can see, at first, things want a buffer from the last filter, so it sends this demand message to this filter. The filter does not have this buffer, so it propagates it up until source. And then source sends the first buffer, which travels the whole pipeline. So it has solved our problem. Now the average time spent by buffer is stabilized. Also, it means that our memory usage is no longer increasing. However, another problem appears here, which is the problem with the throughput. Because, as you could see on this illustration, the elements now are working more like synchronously. At first, sync sends a demand message to the source, and then one buffer is sent from source to the sink. So this is not what we want to have because we do not leverage the fact that we have like concurrent elements that are running. So here is what happens with our throughput. We no longer have the throughput of value like 2 buffers per second, but now it's reduced to not even half a buffer per second. So how can we solve this problem? We can introduce so-called input queue. And here is the illustration of an input queue. So before each element, each processing element, each filter, we want to have a queue, and we want that queue to be of a particular size. So for instance, initially we send some demands so that to fill that queue, and once its size is smaller than the desired one, we also send the demand messages in advance. And here is how does it make our throughput increase. So you can see here like 2 lines. One is orange line and one is a green line. And they describe different queue sizes. And of course, in this very particular case, the pace at which the throughput converges to the desired value is almost the same for both these queue sizes. However, when we take under consideration the average time spent by a buffer in a pipeline, we can see that for a bigger input queue, it's bigger because there are more like places in the queues where the particular buffer needs to wait. So in this particular example, we would of course choose the queue of size 1. However, for your case, you always need to somehow adjust this value of a queue to have the expected result. Okay, however, we remain silent about the fact that sometimes it's not possible for some elements to slow down. I mean, for instance, you might have a live streaming case, and in such a case, you cannot simply tell this data source to send buffers with data only when it's demanded, because it's live stream, yeah? So what can happen in such a case, and how can we deal with it? Well, there's not much that we can do with such a problem. And here is the illustration of this problem, by the way. So this is like our live streaming element, which is, yeah, it is speed. And the solution here will be to simply deal with it and turn the back pressure mechanism off, because it makes no sense to send these demands. So in membrane, we have such a mechanism that when all the sources are in push mode, so the ones that we cannot stop, we simply turn off the back pressure mechanism. However, once a source that is capable of receiving these demand messages appears at the beginning of the pipeline, we turn it on. So this is basically what happens under the hood. Okay, so that's actually almost all I wanted to say today. So if you want to learn more about membrane, I invite you to our website and our GitHub organization. And like the very last thing I wanted to do was to introduce to you a new version of Membrane Core, because you can probably guess that having like a stable API which allows you to create your own processing elements is something we actually want. And it wasn't possible until now, because I would like to do it right now here. So yeah, we'll all participate in the release of the Membrane Core version 1.0 with a first time with a stable API. So let me publish it. Oh, I have already like dry drummed it, so almost. Okay, and here I have like this big button I'm gonna use. Okay, so I think we are ready. Are we? Let's go. Oh, come on. Come on. Wait for it. Yeah.
Okay, thank you, Łukasz. That was great publishing. Any questions? Yeah?
Thank you for your presentation. I'm really excited about Membrane because I hopefully will be able to use it at work. So it's a big thing for me. I wanted to ask you, because you talked about the slow elements. How, if I compose a pipeline, how would you approach in debugging which is the slowest part of the whole pipeline that might be the bottleneck?
Actually, lately we have delivered a kind of tool for Membrane. It's called like Kino Membrane, I believe, because it's a kind of a dashboard that allows you to see some kind of plots that display, for instance, the number of buffers that are produced in given time by a particular element. So of course you would need to consider the fact that like it does not only always mean that when there is like a slower number of buffers processed, that it's something which is unwanted. However, it might be like the clue, like the very first step to find out what's going on there. And you can do it in like real time, so you can always also apply some changes and and see how it reflects.
Any other questions? Yeah.
Hi. So, kind of like GStreamer, but in Elixir and stuff like that. Okay. I have one question. So, I've got a use case that I want to run with you later because it's complicated.
Sure.
But first question, really easy. Does it do things like seeking and transport control, things like that? So, if you have like file sources or things that will, as you said, can generate buffers really fast, and then you have the min flight, and then you want to do something like seeking while you're playing and things like that. Is that handled as well? So it's kind of synchronous. That's why
Yes,
I'm getting at.
actually, you can send some events throughout the pipeline, and they are not like explicitly. They do not need to be joined with some buffers flowing there. So you can, for instance, send some SIG event. We do it with, for instance, a file source when we want to read the MP4 file.
Right.
And we want to skip the mdot part when it's not like the fast start MP4. So it is possible to do so. And you need to more like, because this membrane gives you an opportunity like to create your own elements also. So in case you need to perform such a seeking, for instance, you can write your element in that way.
Right. So what I'm thinking, like, let's say you have 20 files, and they might read at different speeds even. Let's say, and I want to seek while it's playing.
While it is.
Yes, while it is streaming. I want to change the position of where I'm reading from. So I decide like, I'm at second 10, and I want to jump back to second 2.
Actually, I don't think we have like the particular element that is capable of doing so, but it should be possible to do it with the framework.
Right, but the buffers already in the queues.
Yeah, but we do not need to like read all of the buffers to the queue. And actually, once we read it and one is like already in the, you mean you're like concerned about the fact that it might be already somewhere in the input queue of the element.
So will it be aligned again when I seek?
Actually, it won't be, and that is why, for instance, with the case I have mentioned of this MP4 demaxer, because that's where we use this seeking. You need to handle it appropriately in the MP4.
Gotcha. Thank you.
Thank you.